I really enjoyed this conference. I think it's one of the very few where we can really think and talk about neuromorphic processing and platforms and where we're heading. So this talk is it's called Are We the Future of AI? It's because it's a question I kept getting, and now that the talks are on YouTube, like the one from 2 years ago, people have sensed there is something, but the question is, why are we the future? And I think it's a fair question to ask, and where we should go to be truly the future of AI and processing in general. So I think it's always nice to know where we came from. It's a group of people who started thinking in the 90s that there might be another way to do processing. Meet on this piece of mountain in Colorado. This is still going on. I think what matters really is what did go out from this field is two things. One is sensors. And the nice thing is after many years of being on our own, I think every almost company that did these sensors has been acquired or invested by big tech companies. And the other thread of thinking was how to build processors. And after many chips that have been built in the field, now the big players are coming in and are really doing a fantastic job of making these things usable. So the question is, why do we see all these big names close to neuromorphic that used to be really something very discretional a few years ago? And the question is, it's the data deluge. Today, we create more information than we can store. And whatever you want to do, you start by acquiring the information, storing it, computing, and maybe throw it out or not. And you can see it's not sustainable. Today, as Mike said, the game is to process as close as possible to the source of information and avoid this data deluge that is actually ruining many, many things. So back in the days, if you stacked all the information we produced in 1 year in DVDs, you would cover the distance between the Earth and the Moon, and it's probably even more today. So the idea is what I said, we're producing more data than we can store, and it's a big emergency. That's why everybody's investing in neuromorphic. So why neuromorphic? So neuromorphic is due for these two reasons in red today that we hear about it so much. These cameras promise the low power, low latency that is currently lacking in vision, and these sensors are promising the low power inference or computation that goes with it. Because these sensors are truly fantastic. They are highly light independent. They go super fast. You can process everything as it comes. And from the other side, I think the industry has reached a level where you cannot go beyond the current processing. So I think everybody knows about this. So now you've bought yourself one of these beautiful cameras. They're all available. You can buy them all over the place. And so what do? Well, you have events coming, spikes, and information gets when you get it. And if nothing happened, you get nothing. So all this is absolutely perfect in solving that goal of low latency and low power. So now what do? Most people have two options today. One is you go to a CPU and you send your event as much as possible. You're increasing hugely latency and play with time and do proper event-based algorithms. The other option you have is to go to a GPU, and lots of people take the beautiful advantages of this camera, try to generate a frame because these things are built to process frames and just do what we were doing before. So it's not really, this path here, I think, is just not the way to go, as mentioned by Mike. So now if you look at these sensors, this is an event-based camera mounted in a car. This is the amount of data you're producing while being 1 microsecond time precision. And in red, several orders of units, log units above is how much you would generate and require a memory if you are using a 30 image per second. It's huge. So you can see that what you'd like is something that can make sense of all these very sparse amount of data in the best way, and keep playing with few hundreds of events because that's cheaper. So we've done a big survey. This paper should go at some point. And the most important line in this table is we've been through all, as you can see, the poker DVS, the NMNIS, the DVS gesture, all available databases that people use in this field. And what you can see is, suppose you are interested in information, in temporal information at the scale of 1 millisecond or 10 millisecond, which is mostly what people usually play with. You can see here that your memory load, whatever you're going to do, is going to be 8% to 30% that if you were really generating frames, even at this rate, which is truly amazing because the data is so sparse that if you are allocating that good memory inside, it's a waste of resources. All those resources, in the most cases, will be used by to 8%, which is truly wasteful because it's burning energy, it's slowing you down. So when you see these numbers, you realize that, yes, neuromorphic event-based sparseness is the way to go. The problem is, why aren't we there yet? So I'm not mentioning all the academic work that happened and still happening here, but that's it. These are really things that happened lately between IBM, between the work in Loy, which is remarkable. And it comes, as I showed you, from that piece of mountain where historically we thought like you want to build something to process events where you have to copy the brain. And so our approach currently is to replicate, which is fine. I mean, we have to start somewhere. We have good neuroscience knowledge, much more than before. And the question is, would it be better, as somebody mentioned before, is it better to understand what if we really understood the brain, what will we be building? Will we be building, silicons and a neuron in silicon, or would we build something closer to an airplane than to a bird? This is an open question. Today, as somebody mentioned, Terry defines many levels in which we can tackle the brain, from the mass of at different scales, from centimeters to micrometers. And every scale is really legitimate and allows you to ask yourself deep questions. So where is that scale of abstraction we need? And so it's interesting to see that neuromorphic is a very old story. And basically everybody who contributed to make things move forward have always, in this field at least, tried to copy the brain. So initially people thought the brain was doing logic. And then suddenly we got this idea with the perceptron that led to what we have today, which is weights are important. Unfortunately, we know much, much more about the brain today. But in the 80s, there was even a business of people trying to accelerate MLPs and stuff like this. And it failed because it was not answering what people were wanting. And it was not doing the job. So I think the main question we have the hardest part, I think, is for those who know microcomputers, when they started, everybody had to code and to type. And when you opened the computer, it was flat, there was nothing. But here, the question is, we are starting a new field, we are starting a new computation paradigm. And the question is, how do you encode numbers? I think that everything is going to be turned out into this problem. If you express numbers nicely with these neural chips, you're going to open the field to everybody because you'll be able to compute asynchronously, as I showed, but also do lots of things in AI. So how do you encode numbers? And if you look at what's happening in neuroscience, they will tell you, honestly, this is the nicest work I've seen out there. The brain has a notion of numerosity encoded in neurons. And so neurons react to 1, to 3, to 4, to 5, to numbers, whatever you see, 5 cars, 5 birds, 5 humans. But this is not the way to go because you cannot put a set of neurons behind every number, which would be absolutely undoable. So there are basically two ways to encode numbers today. First one is using rate. So these are all different types of neuron. This is the stimulus from -1 to 1. And this is the rate, how much spikes you're going to get per portions of time. And so the idea is to find the right weights and sum these spikes to get numbers out of it. And it's using the base approach. So you do any signal, you decompose it into these sets of functions because neurons fire in a very discrete manner, very repeatable manner. And this is a rate-coded approach, which is doing the job. It's also allowing amazing things like learning. You can do amazing learning with these frameworks, and it's currently widely used. The other approach is if you inject more neuroscience, you realize that most of what we think is computing, is being computed by a neuron is done by its synapses. Synapses are very diverse. Spikes are not binary, they come with some kernel, and the integration of this kernel puts all the computation in the time domain. And it's, I believe, from recording real neurons, this is how most of the computation is happening. And the other thing that really we know today, and I don't think this is accepted until like maybe a decade ago, that time is super important. Time and delays are what makes most of the computation out there. So if you add all this, you boil up to see how do I encode numbers? Well, if you see here, a number can be a duration, a time duration between spikes. So here you have 2 units as the most simple way of encoding a number. 2 delays, this unit excites the other unit. One path is faster than the other, you get 2 spikes, and those 2 spikes encode the number. So when you get into that, your units look like something that's not very common today. Lohi allows this, and this platform now is available on Lohi. So you have, when events come or a spike come to this unit, you start some integration, and this paper shows that for a 3 set of linear, non-linear, an absolute direct change of the membrane potential, you can literally compute anything. You can do multiplication, addition, logic, and start having micro-instruction and put them together. So how is this working? So this is a very simple network. It's called a memory, but an inverted memory. So this is a number you want to store in this thing. And as you see, synapses are colored according to their what type of synapse it is. And as you can see, the whole game here is that a time duration starts an integration that will give you some value. And when you trigger again and you trigger another accumulation, integration, you get another number. So the whole game is how do you slow down, how do you go from one quantity to another by playing with these kernels, by integration time, by delaying stuff, by accelerating stuff, by playing with the weights, so that you can get this type of computation. And this is quite efficient because you need very little numbers of neurons to do many things. And you can even go from typing a procedural language and transform it into micro instructions. Here you see an optical flow. It's running an equation that you find in one of my papers. So with this being said, there is, if you look at the other things my group is producing, the same mindset, there is something where you want to learn events. So of course you can use backprop, which I don't think is really adapted to these things. There's a whole debate whether backprop is the way to go for spikes. But suppose you want to learn whatever the structure of spikes, blue, red, and this guy that just came here last. The idea of dynamic synapses allows you really to have a unique, I would say, descriptor, so that you can have learning that happened there and you can go deep, very deep. This is also put on Lohi recently. And you can go as deep. So you can basically on the same chip have conventional, like general purpose computation, and you can do learning. Now, this being said, what is really driving the field today is what people call neuromorphic vision. I don't think people here are part of this community. It's all what's happening in CVPR, ICCV, like the hardcore computer visionists. And these guys, of course, are interested in learning, but most of them write equations, like SLAM, like the way we used to do it before, but we do it in the time domain. And when you start doing this, you're left with not much to process. Today, most of the market wants to do SLAM, wants to do tracking, wants to do all sorts of things where you are writing equations in the time domain. And anything I've mentioned before is not really answering this. So, and this is crucial because this is what's going to be in the mobile phone. This is what's going to be in drones because I put some names here. People are known to play with drones and etc. And these are the leftovers, and these are the guys who are currently in need of a processor. So there is no doubt that the future is ours. No doubt. We have the best sensors. We have the best paradigm change and promising. We have the brain. It is working. So it's just a reverse engineering problem. But today, what we need and what is really driving, I would say 50% of the field is something that could execute learning and general computation, meaning people want something accessible they can program very easily. And also the other thing is you want something that allows you to do incremental processing. You don't want to do frames because you're going to lose all the advantages. And I personally think each step you do to link yourself to what happened before is somehow wrong, because everything we've done was developed on old ideas. And the other thing that is killing all sorts of computation on CPU today when you write your equation is, how do you get neighborhoods around an incoming event? I'm almost done. This is my last slide. And then the other thing is you want to be sparse, very sparse memory use that could adapt itself, because sometimes you don't need to allocate everything. And finally, as we speak, there are people looking for how to handle 5 giga events per second to do computation at the budget of few milliwatts. These numbers here are what we need to solve and address, because that's our future. That's where the future is heading, as I mentioned. So I'll stop here. Sorry again for technical problems.
Don't worry. Thank you for this great talk.
Thank you.
And Johannes Schemmel, who is from Heidelberg, and he's, thank you, already sharing his slides. So Johannes, the floor is yours.
Thank you, Björn. My talk now is called Exploring the Possibilities of Analog Neuromorphic Computing with Brain Scales, and it's somehow complementary to what we've heard so far, because it's also event-based computing, but it goes one step further than Loihi.